Hello, am I audible? Hello, hello. Is my screen visible? Thank you. So, good afternoon, everyone. Welcome to this NPTEL live session for the course Introduction to Machine Learning. This is week 11 of this live session. My name is Oyan Maiti. I am a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So in this live session I will discuss some practice problems on week 11 content. The topics were Gaussian mixture models and expectation maximization algorithm. These are the topics, so I will discuss some practice problems on these topics, and then I will also try to answer your questions and doubts. So if you have any questions or doubts, you can ask me after that. So we can start the problem solving part of this session. So this is question 1. In each of these options, the diagram contains a log likelihood function for a particular problem, as well as the initial value of the parameter used in the execution of the EM algorithm or expectation maximization algorithm. So you can see there are 4 options and 4 graphs are drawn there, and for every graph we have this theta initial, which is the starting value of the parameter, and in which of the given scenarios will the EM algorithm be able to achieve the global maximum. So these are the log likelihood functions, these are our objective functions, and in which of these 4 options it will the EM algorithm will be able to find the global maximum or reach the global maximum. You can write your answers in the chat. I am not able to hear you properly. Can you please repeat?
I said I have not studied this yet, so I won't be able to answer. If you wish to, you can proceed.
Okay. Yeah, but this was last week's content, right? The assignment deadline is also passed, isn't it? For this content. Okay. So anyone else? Has anyone studied this and can answer this? So in this question, the log likelihood function is given, and EM algorithm is an optimization algorithm. So it tries to find out the global maxima or global maximum in a log likelihood function or in any objective function. So in every option there is an objective function is drawn here, and theta is the parameter that we want to find out, with respect to which we want to find out the maximum value of the objective function, and this is the initial value of the theta. These are the initial values in different options. So as we can see in the first option, the theta or the parameter starts here, and expectation maximization algorithm will be able to take this theta value to this maximum point, but after that it will not be able to go past this. So it will end up here, and this is not the global maximum point. Global maximum point is this one, and it will get stuck to this local maximum point. So this is a local maximum point, and it will get stuck here, and this is a known problem for EM algorithm, that it might get stuck in a local maximum point and it will never be able to achieve the global maximum. So first option, we can say that it will not be able to achieve global maximum for sure. And now in the second option, so it starts here, and it might go to this point or this point. So there are two possibilities. So if it goes to the right this way, then it will be able to find the global maximum, because this point is the global maxima, as you can see from the plot. But if it goes to the left, it will reach this point, which is a local maxima, but it will not be able to reach the global maxima anymore. So option B is also not right. Option C, we can see that this is the initial parameter value, and it will be able to reach this global maxima, because there are no other points where the derivative value is 0, or it is a local maximum or minimum point. So it will eventually go to this global maximum, and it will be able to achieve the global maximum using this EM algorithm. So option C is correct answer here. And if you observe option D, so in option D it starts at this point, but this point is again a global maxima, local maxima. So it will be stuck at this point, and it will not be able to go to this global maxima. So it will get stuck at this point, and it will not achieve the global maximum. So option D is also not right. So the only correct option is option C. So only in the scenario C it will be able to achieve the global maximum point. So this is how we can find out whether the EM algorithm will be able to find the global maximum or not. So option C is not right. It's not right. So you can see that in each scenario other than C, the EM algorithm will get stuck in a local minimum. So that is the problem. Yes.
In diagram B, if there wouldn't have been that small local optima, then would it have been reached?
Yeah. So in B, it can go either right or left.
D.
D.
D is understood. Yeah.
D. Okay. Yes. In D, it will reach up to this point, and in this point, the derivative value would be 0. So it will it will not be able to overcome this point, and it will not reach there. So because
if this local optima was not there, if this slope was straight till top, then would that also have been a correct option?
In this case, this is a local D, right? D.
Yeah, only in D diagram, if that local optima was not there.
Yes.
If it directly was that upgoing graph.
Yes.
Then would that have been a correct option?
Yes, if it had been like this, then it would obviously be able to go to this peak, and that would be the global maximum eventually. But here we can see that this is a local maximum point, so it will get stuck there. So you just have to find out whether it might get stuck at a local maximum or minimum or not, and if it gets stuck, then it will not be able to achieve the global maximum point. Okay. So this is question 2. What are the necessary conditions for this expression? This is a probability density function. This is an expression about a density function, and what is the necessary condition for this expression to be a density? And there might be multiple correct answers here. So we want this expression Pxn to be a density or probability density function, or PDF as we call it. So what are the necessary conditions for this? In which cases it will be density, and in some cases it might not be a density. So this is based on Gaussian mixture model. So these are the different Gaussian distributions, and this is the mixing coefficient, and we are mixing different Gaussians and creating a mixture of Gaussian, or the Gaussian mixture model. So in this question you have to find out what are the necessary conditions for this pxn to be a density, and pxn is given by summation over pi k, which is this pi k is the mixing coefficient for different Gaussians, and this is the probability density function for individual Gaussians. So this is for the kth Gaussian, and pi k is the mixing coefficient for the kth Gaussian. So the necessary condition for this is that these pi k coefficient mixing coefficient values should be between 0 to 1. If it is not, then this expression, this whole expression would exceed would not be a density, because for a density, for a function, if fx is a density, only if this fx dx from minus infinity to infinity equals to 1. So this mixing coefficient has to be between 0 to 1, and the other condition would be this one, that summation over pi I should be equal to 1. So these are also probability distribution. This pi k is also a probability distribution. So summation over all the pi values should also be 1. So that's why A and D, these are the two correct answers here. So these are the two necessary conditions for this expression pxn to be a density function, A and D.
Is the given equation a standard equation for Gaussian mixture model, or do we expect any other variation of that equation?
No, this is a general expression for the Gaussian mixture model. So there are so we have this k number of Gaussians, and pxn given theta k, this is the density for individual Gaussian. This is for the kth Gaussian.
Yes.
And pi k is for the mixing coefficient for the kth Gaussian.
Yes, yes, I understood what you explained.
Yes.
Could there be any other question on that question? Any other possible question?
On this equation?
Yeah.
No, I don't have any other questions on this equation for today.
Okay. Okay.
And now moving on to question 3. So there is a figure on the right side, and this is a Gaussian mixture model or GMM model, and you have to find out the value of k. So k is the number of Gaussians in the mixture model we have used. So a Gaussian mixture model is given in this diagram, and you have to find out k, which is the number of Gaussians used in this Gaussian mixture model. Keshav Banka says 4. Okay, so value of k is 4, he is saying. Any other answers?
Explain how to find out the value of k, then perhaps we will be able to.
Okay, yes. So in this diagram, this is a Gaussian mixture model diagram. So these dots are points, and these contours, this one, this one, this one, this one, these are the density of the mixture of the Gaussians. So from this diagram you can see that this is one Gaussian, this is another Gaussian, this is one more Gaussian, and this is one more Gaussian. So these are the 4 Gaussians that are used in this GMM model, and after mixing this we are getting these contours, this one, this one, and then this one. So these contours represent the density of the mixture model after mixing all the Gaussians. This one. So this is how the Gaussian mixture model works. So in this model there are 4 Gaussians, this one, this one, this one, and this one. So these are the 4 Gaussians used, and after mixing these 4 Gaussians we get this density of the Gaussian mixture model. So what Keshav has written in the chat is right. So 4 is the correct answer.
In this type of problem, the number of contours and the number of Gaussians should be equal.
Number of contours, yeah, the smallest contour you have to see, this one, this one, this one, and this one. They are the 4 round shaped contours individually you can find out, and then after that these contours should become combined. This is whole one contour. So
yeah, so these outer contours and these inner circles, they should match, no number, like 4 outer and that's the 4 circles that we are doing.
no, I mean, are you telling that this is 1, this is 2, this is 3, this way you are
Yes.
No, I mean, no, these can be any number of contours. You can have any number of contours. This is just to show you the shape of the density function. There can be much more like this, like this. This just show you the density shape of the density function. So you have to visualize it along z axis, which we cannot show in this 2D. So you have to find out how many small circular clusters you can find out. This is one, this is one, this one is another one, and this is another one, isn't it? So 4 round shaped clusters you can see from the data.
Okay.
So you have to find out those how many clusters we can see from the data. So this is one, this is one, sorry, this is one, this is another one, and this is one more. So it has used 4 Gaussians. You don't have to think about this outer contoured lines. This is just to show you the shape of the mixture of Gaussians. You just have to find out the number, how many clusters you can see from the data. So in this case it is 4. So 4 is the correct answer here. Yeah, so it will be equal to the number of clusters you can see in the figure. That will be the value of k and the number of Gaussians that you will consider for that. Now moving on to question 4. This is again on the same diagram. So the diagram remains same. Now the question is, what is the minimum value of k dash which is not equal to k, where k is from the previous question. So in the previous question k equals to 4 as we have seen. So what is the minimum value of k dash which is not equal to k, for which you will get a very similar density estimation. So basically we want to reduce the value of k and still we want to retain the overall structure of the Gaussian mixture model, as we can see from this diagram. So the contour lines should almost be similar, but we will be able to reduce the value of k, the number of clusters or number of Gaussians. Keshav Banka has written 3, which is option A, 3. Rightmost clusters will become 1. Okay, so Keshav is saying 3 is the right answer. Any other answers? So basically we want to reduce the number of clusters or number of Gaussians, which is same as minimizing the or reducing the value of k, but the density estimation or the density function would look very similar to using 4 clusters or 4 Gaussians. So in this question, again you have to analyze it from the figure that is given. So this is one Gaussian which you cannot reduce. So this is separated from all other Gaussians. So this one would remain. This is also almost separate from the other two. So this is the second Gaussian. But you can combine these two Gaussians. So you can combine these two Gaussians into one. So this would represent, these two would be combined to only one Gaussian. So it would be 1, 2 and 3. So you can minimize the value of k to 3. So the value of k dash in this answer, in this question, would be 3. So basically you have to see whether you can combine multiple Gaussians into one or not. So you can see that this first Gaussian, it is separated from all other Gaussians, so you cannot combine it with the others. The second one is also very much separated from the others, though it is connected to the third Gaussian also, but still it is very much separated. But the third and the fourth Gaussian you can combine into only one. So it makes only one Gaussian out of the two small Gaussians. So it will be the third Gaussian. So this way you have to find out. So answer would be 3. Option A, 3. So basically you have to see it from the, observe it from the figure. Option would be, answer would be A, 3. Now question 5, and this question is also again on the same diagram for the Gaussian mixture model. And so assume equal pi I, which is the mixing coefficient for the Gaussian mixture model. So we are assuming equal pi I for each Gaussian model after convergence, as in question 2. So it was what was sorry, this would be question 3. Yes, it should be question 3. So there in question 3 we found out the value of k to be 4, and we assume that the value of pi I is equal. So the pi for 4 different Gaussians would be 0.25, 0.25, 0.25, 0.25. So we are assuming equal pi I values for each of the Gaussians, and there are 4 Gaussians, so it will be 0.25, 0.25, 0.25, 0.25 for the 4 Gaussians. What would be approximately the values of the pi i's for the model you will get with k dash, as in it was in question 4. So k dash should be 3. So k dash was 3 in the previous question. So after minimizing the value of k to 3, what will be the pi I? So previously we had 4 Gaussians, so we would have 4 values in pi, and now we have 3 Gaussians. What would be the mixing coefficient values? So there would be 3 values now for sure, because k dash is 3, so we have 3 Gaussians now. So what would be the pi i's now? Keshav Banka says option C, which is 0.25, 0.25 and 0.5. Okay. So anyone else? So there would be 3 values in the pi i's now, because k dash is 3, that we have found out in the previous question. So pi i's would have 3 values now. So previously the values were 0.25, 0.25, 0.25, 0.25, so equally distributed between 4 Gaussians. So now we have in the previous question we have seen that this is one Gaussian, this is one Gaussian, and we have combined these two into, so this is first, this is second, and this is third. So these are the 3 Gaussians that we have found out in the previous question. That is why k dash is 3. So the pi I values would be, so first Gaussian remains the same as the previous question, second Gaussian is also the same 0.25, but we have combined the last 2 Gaussians into only one Gaussian, third Gaussian. So now these 0.25, 0.25 values, these 2 values would be combined, so it would be added, and 0.25 plus 0.25 would be 0.5. so we have combined these 2 Gaussians, so the mixing coefficient values for these 2 Gaussians would be added up, so it would be 0.5. So pi I would have 3 elements now, so 0.25, 0.25 and 0.5. so this 0.5 is basically because of this Gaussian, because we have combined 2 individual Gaussians into one single Gaussian, so we have to also add the values of the mixing coefficient values, which were 0.25 and 0.25 for the third and fourth Gaussian. So we add these 2 up, so it would be 0.5 now for the third Gaussian. So this is how we will find out the mixing coefficient. So option C is the right answer.
So in these type of questions, we always divide the number of clusters by what? I mean, 1 divided by number of clusters.
No, I mean the question is given that equal pi I. So assume equal pi I for each Gaussian. So pi I can be in any form, but pi I summation over pi I has to be 1. So pi i's can have any values, but we are assuming equal pi I. So 1/4 for each Gaussian. Thus, and after combining these 2 Gaussians, we are getting 0.5 for the third Gaussian. So solution is C, and the detailed solution is also given. So for k equals 4, we are assuming equal pi i's. So pi i's would be this, and for k equals 3, two of the clusters are merged. So these 2 were merged. So that's why these 2 mixing coefficient values will also be added. So 0.25 plus 0.25 would become 0.5. So that's why the pi I is getting changed, and this is the new pi I. This is question 6. This is again on Gaussian mixture model. So again a figure is given. This is again there are multiple Gaussians, and the density function is represented using these contoured lines. For a set of points given in orange, so these orange points are the data points that we have. The density estimation of a GMM is given below. So for these orange data points, the a GMM is produced, and the density is given by these contoured lines. And the question is, what is the problem evident in this image? So this is not exactly right. This GMM is not very good in nature. So what is the problem with this GMM formulation for this diagram? So there are 4 options. First option is pi i's are too big. Option B is the clusters are not sampled from a Gaussian distribution. The GMM has not converged yet. And option D is there is no problem in this GMM. So what is the problem evident from this GMM density diagram? So these are the contoured lines. This is one, this is one, this is for another Gaussian, and these are the combined contour lines, this one and this one. Keshav Banka says option B, which is the clusters are not sampled from a Gaussian distribution. Okay. Okay, so is there any other answers? Anyone else? So in this question, so these orange dots are the points. So we can see there are 2 sets of points. So this is one set of points, this is another set of points. So none of these sets look like a Gaussian, isn't it? So but we are using Gaussians to represent each set of points, so that's why we are taking 2 Gaussians. This circle is one Gaussian, this circle is representing another Gaussian. So we are using 2 Gaussians to model each cluster here, but the clusters are not Gaussian shaped. The clusters are this narrow shaped something, so these are not Gaussian like. So Gaussian would be if the points had been like this. So they form this round shaped cluster or oval shaped, something like this. If they form something like this, then you can represent this set of points as using a Gaussian distribution. But here these clusters are not Gaussian shaped, you can see. So the problem evident here is that the clusters are not sampled from the Gaussian distribution. So Gaussian is not a very good method to Gaussian can be used, but these 2 Gaussians are not enough to find out the underlying distribution for the data points. So that's why this one Gaussian, but there are no points in this region for that cluster. all the points are here, so this Gaussian is not perfect to represent this set of data points or this cluster. So that is the problem, that the clusters are sampled from clusters are not sampled from a Gaussian distribution.
Could you explain the relevance of point A in this? Pi I is our to this.
I mean the pi I is
Understood.
the pi I is we have not even used here, so that's why pi I here we have taken I think half and half using this, because these two Gaussians are equally shaped. So most probably the pi I's are half and half, but we have not mentioned anything about pi I's, so that option is not very relevant because we don't have any information about pi I's in this question. So the most the best answer would be that the clusters are not sampled from a Gaussian distribution.
In general, how much do we consider pi I for any given questions?
Summation over pi I should be 1. Now the pi is again a parameter of the mixture model, so it will be learned by the mixture model. So you can start from any value and it will eventually converge to some value. So these are not the values that you fix, these will be computed by the algorithm based on the data distribution from the that you get from the data points. So in this case the option is B, so the option A is not right. Now question 7, this is again on the same diagram as in the previous question. So for this set of so what can be done to get a better fit? So we have seen that there is a problem with this diagram. Using these two Gaussians there is a problem. So what can be done to better fit this set of points? So 4 options: increase k, is the number of Gaussians or the number of clusters that we are considering. Option B is use of better initialization. Option C, learn for more iterations. Option D, there is no problem. So in the previous question that we discussed that the two Gaussians are not able to find out the actual data distribution, so the clusters are not following Gaussian distributions here. So what can be done to rectify that problem? So Keshav Banka says option A, increase k. We will need a Gaussian for every point or a group of very few points. Okay. Anyone else? Any other answers? So as we have seen in the previous question that this cluster is not Gaussian shaped at all, or even this cluster is not Gaussian shaped at all. So we cannot represent this cluster using a single Gaussian distribution. So also this cluster cannot be represented using only a single Gauss distribution. Even this cluster cannot be done. So what can be done is that we can increase the value of k and pick very few points, and so each group, this one, we can represent every group as a Gaussian. So the value of k basically increases, the number of Gaussians that we consider would increase. So that way by increasing the value of k, we will have many more Gaussians. So every Gaussian would be very few points in the neighborhood, and that way we will be able to get a better fit for this data points. So option K would be the correct answer. So basically we have to increase the number of Gaussians that we are considering. We cannot consider only one Gaussian for one cluster only, because the clusters are not shaped like Gaussian or round shaped or even oval shaped. So we cannot represent one cluster using a single Gaussian. So we can increase the value of k, and those very few points would form a Gaussian eventually, and we will be able to represent each group of points using a Gaussian. So that will be a better fit. So option A is the correct answer, and this diagram is shown for k equals 8. So if we consider 8 Gaussians, so this is one Gaussian, this is one Gaussian, this is another one, this is one, this is one. So 4 Gaussians from one cluster, and again one from here, here, here and here. So 4 Gaussians from each cluster, so total 8 Gaussians we are considering, and this is these 8 Gaussians are able to model the data points much better. So this is how we can represent the data distribution by increasing the value of k. So option A, increase value of k, is the correct answer. So here we have taken k equals 8, and if we take k equals 10 or k equals 16 or even more than that, so it will be even better, but the number of Gaussians are increasing, so number of parameters would also increase, and so you have to find out a trade-off between that, because if number of parameters increase, then your the complexity of your algorithm would also increase eventually, and that might not be better in some cases. So you have to have a balance in that. So here we have considered k equals 8, but if you consider k equals 16 or 20, 25, then it will be even better. So increase k is the correct answer to better fit the data. Question 8. What does soft clustering mean in GMMs? GMM is Gaussian mixture models. So basically what does soft clustering means in GMMs? So there are 4 options. There may be samples that are outside of any cluster boundary. The updates during maximum likelihood are taken in small steps to guarantee convergence. Option C is it represents the underlying distribution to be Gaussian. Option D is samples are assigned probabilities of belonging to a cluster. So there are the 4 options, and you have to find out the answer for what does soft clustering mean in GMMs. Keshav Banka says D, which is samples are assigned probabilities of belonging to a cluster. Soft clustering basically means that every point can belong to multiple clusters with some probabilities. So we assign probabilities of belonging to a cluster. So for every point, if there are 5 clusters, every point will have 5 probability values of being assigned to 5 different clusters. This is what soft clustering means. So option D is the correct answer, that samples are assigned probabilities of belonging to a cluster. So in contrast to this, we have hard clustering, like k-means and some other algorithms, and even the hierarchical algorithms. So every point belongs to only one cluster. Even density based algorithms, every point belongs to only one cluster and it cannot belong to any other clusters. But in soft clustering, each point can belong to multiple clusters with some given probability. So in GMM, this is what happens, that we use soft clustering, and each point can have can belong to multiple clusters. So option D, that samples are assigned to multiple probabilities of belonging to a cluster. Option D is the correct answer. Question 9, what is the update for pi k, which you have seen, the mixing coefficient, in EM algorithm for Gaussian mixture models? So there are 4 expressions given for update of pi k, and this m is the iteration number, so it's mth iteration, and n, this n or this n, these are for nth point, and m is for the mth iteration, and k is for the kth Gaussian. So all these are standard notations. So if you have gone through the video lectures, you will be able to understand the meaning of each term here. Keshav Banka says D, C, okay. So each of these options are very similar. There are very small differences, so you have to be careful about that. Keshav Banka says, can't we write gamma ZNK as gamma NK as shown in the start of lecture? Yeah, I mean gamma ZNK and gamma NK are exactly same thing we are trying to say. So gamma ZNK and gamma, you can also write it as gamma NK. In some books they write it as gamma ZNK. Z represents the cluster or the Gaussian. So these two are exactly same. So here the correct answer is option C. So it's pi k at the mth iteration will be updated as summation over n equals 1 to capital N gamma z n k given is v a minus 1. This is the parameter for this gamma, which is the responsibility. This is the gamma is also called the responsibility. Gamma is actually gamma z n k is actually the probability z n equals k given x n and parameterized by this v a minus 1. So this is also called the responsibility, that a given point x n belongs to the kth cluster. What is the probability of that? And this v m minus 1, this is the parameter for this probability distribution at m minus 1th iteration, and this is the expression. So you have to be careful that in the denominator we would have n, not n minus 1. In some of the options it is given as n minus 1, so it would not be n minus 1, it would be n, and this iteration number for this v would be m minus 1. So using the parameter values at m minus 1, we are updating the value for pi k at mth iteration. So we are using the value of m minus 1th iteration for update in mth iteration. So that's why this value would be m minus 1. So option C is the correct answer. Question 10. KNN is a special case for GMM with following properties. There can be multiple correct answers here, so you have to select all of them. So KNN can be thought as a special case for GMM using some specific values of the parameters of the GMM. So which are these special cases? So first option is gamma I equals I by 2 pi epsilon to the power half e to the power minus 1 by 2 epsilon. Option B is covariance matrix is epsilon into I. So this I is the identity matrix. So basically covariance becomes constant. So this is what it says. So covariance matrix becomes constant. Option C is mu I equals mu j for all ij. Mu I and mu j are the mean values for I and jth Gaussians respectively. And option D is pi k equals 1 by k. So basically it is equal distributions, it's saying. So each Gaussian would have equal pi I values. So there can be multiple correct answers here. So which of these options is or are correct? Keshav Banka says B, covariance equals epsilon I. Okay. Anyone else? Any other answers? And also it is a multiple correct answer question, so there might be some other correct answers also. Keshav Banka says D, so he says B and D. These are the two correct answers. Okay. Anyone else? So here the correct answers are B and D. So they are the two correct answers. So KNN is K nearest neighbor. So the covariance becomes constant in this case. So covariance is no more a parameter which is learned by the algorithm. So we if we make the covariance constant, then it becomes very similar to KNN. And also in KNN, the pi k, which is the mixing coefficient, is equally distributed. So because we just try to find out the k nearest neighbors, and then we take the average of it, or if for regression and for classification we take the majority of the k nearest neighbors. So that's why the mixing coefficient is equally distributed. So these are the two correct options, B and D. So if we follow these two properties, in that case GMM becomes KNN. So KNN becomes a special case of GMM. So now moving on to question 11. Suppose we have a Gaussian mixture model of three-dimensional data with four components. Components means four Gaussians. So we have four Gaussians basically. We use a model with full covariance matrices. So how many parameters are there in this GMM model? So the data is three-dimensional. So each data point has three dimensions or three features, and we are considering four Gaussians. So k is 4 here. So this is basically 4. K equals 4 Gaussians, and we are also considering full covariance matrices. So in that case, how many parameters will be there in this GMM model? So has anyone come up with the answer? there are three types of parameters in a Gaussian measure model. So we have these pi values, we have mu values, and we have this sigma values. So pi is the mixing coefficient, mu is the mean for the Gaussians, and sigma is the covariance matrix for the Gaussians. So the data is three dimensional and there are four Gaussians. So in pi we will have one value for every Gaussian, so there will be four values in pi. Then mu, so mu is the mean for one Gaussian. So the data is three dimensional, so mean would also be three dimensional. So there are three values for every Gaussian, and there are four Gaussians, so 12. So three dimensional for four Gaussians, so 12. Sigma, now sigma is the covariance matrix. So the covariance matrix is so we just have to find out the number of parameters only in the upper triangle or lower triangle of the covariance matrix along with the diagonal values. So this is three dimensional matrix, so it would be 3 into 3 plus 1 by 2. So the number of values only in one side of the diagonal of the matrix. So 3 into 3 plus 1 by 2, so it will be 3 into 4 by 2, which is 6. So 6 values for every Gaussian in the covariance matrix. So there are 4 Gaussians, so 24 parameters would be there in the covariance matrices. So 4 plus 12 plus 24, so that would give 16 plus 24, 40. So 40 is the correct answer. So this is how you have to find out the number of parameters. There are three types of parameters: pi, which are the mixing coefficient values; mu, which are the mean values for Gaussians; and sigma, which is the covariance matrix for one Gaussian. And also you have to multiply each of these values with the number of Gaussians, like this 3 into 4 and here 6 into 4, and 4 the pi value is already 4, the number of Gaussians. So that way you have to find out the number of parameters. So in this case it would be 40. So B is 40, and the explanation is also given, so you can go through this. I'm not able to hear you properly. Can you please repeat once? No. There can be one more variation, that instead of using this full covariance matrix, we are using only a diagonal matrix, diagonal covariance matrix. So only the diagonal elements would be present in the covariance matrix, and the all other values would be 0. So in that case, the number of parameters from the covariance matrix would be reduced. So here we have considered these many values from the covariance matrix. Now if we consider only the diagonal values, then it is three dimensional data, so it would be 3 here. It has been calculated as 6, so it will be 3. So in that case it will be 3 into 4, for 4 is the number of Gaussians, so 12 it would have been. So this can be one variation of it. Is it okay?
But actually, I'm not having the full knowledge of that covariance matrix and how to calculate. Maybe because of that, I'm not understanding in depth.
Yeah, once you go through the lecture videos properly and the materials, you'll be able to understand that this calculation is very easy. So you just have to understand what are these different parameters are, and what are these. So in that way you will be able to find out how many of them would be present in the model. Now question 12, this is the last question of this session. Which of the following correctly describes the difference between EM for mixture of Gaussians and k-means? So EM for mixture of Gaussians, this is one algorithm that we can use for clustering, and k-means is another algorithm that we can use for clustering. So what are the main differences between these two? And there may be multiple correct answers here. So option A says k-means often get stuck in a local minimum, while EM tends not to. Option B says EM is better at capturing clusters of different sizes and orientations. C, EM is better at capturing clusters with overlaps. D, EM is less prone to overfitting than k-means. Keshav Banka says C and B. Okay, C and B. Anyone else? Correct answers here are B and C. So option A says that k-means often gets stuck in a local minimum, while EM tends not to, but it also sometimes gets stuck in a local minimum that we have seen in the first question, that it might get stuck in a local optimum point. So that is also a known problem for EM algorithm. Option B says EM is better at capturing clusters of different sizes and orientations, and this is right. That in k-means we have already seen that k-means only recognizes round shaped clusters because it uses Euclidean distance. So it is not able to capture clusters of different sizes and shapes. So from that point of view, EM can recognize or capture clusters of any shape and sizes. So this is an advantage for EM. Option C is EM is better at capturing clusters with overlaps, and this is also right. So in using EM for Gaussian mixture models, we can find out soft clusters also. So different clusters might overlap, and every point might belong to multiple clusters. So option C is also right from that point of view. Option D is EM is less prone to overfitting than k-means. This is not completely verified. So option D we cannot say, but option B and C are obviously correct. So option B and C, these are the two correct answers. EM is less prone to overfitting k-means, which is not verified, and k-means often gets stuck in a local minima while EM tends not to. This is not correct. EM also sometimes gets stuck to local minima or maxima points. So B and C are the two correct answers. So these are the practice problems that I wanted to discuss today. So now if any one of you have any other questions or doubts, please feel free to ask me. Keshav Banka says, can you please show question 1 later? I missed it.
Could you please understand the configuration between the given set of points, then how to find the MLE for different types of distribution?
Given set of points, you want to find the MLE.
MLE for different distribution.
Yeah, so for MLE, so if you have x1 x2 like this xn points, and you are given a distribution, for example fx. So for MLE you have to find out the first, write the expression, or the log likelihood expression you have to write. So log likelihood would be the log of product of fxi I equals 1 to n. So this fx is the density function. So basically you have to multiply fxi for I equals 1 to n and then take the log value. So this is your log likelihood, and for maximum log likelihood you have to, if this is L, L of theta are the different parameters for this density or distribution. You have to find out the derivative for this L theta and set it to 0. So now fx can be any distribution. You just have to plug in fx here, find out the product from I equals 1 to n. So n points are there, x1 to xn. You have to find out the product, take the log, and then you will end up with this log likelihood expression L theta. So this log likelihood will be a function of theta only, and now your theta is the parameter for this distribution that will be given to you, and you have to differentiate L theta with respect to theta and set it to 0, and you are solving this expression, you will be able to find out your desired theta values. Is it okay? You just have to replace this fx with the given distribution. Okay, so question 1, Keshav is saying, question 1. No, yeah, if you have no other questions or doubts, you can leave. Thank you. So in question 1, so there are 4 diagrams given for EM algorithm. So in each of these diagrams, a log likelihood function, which is our objective function, is drawn, and the initial value of the parameter theta is also given here. You can see this theta here, this one. So these are the initial parameter values. So we start from here, and these are for the log likelihood function, which is our objective function. So now in which of these given scenarios will the EM algorithm be able to achieve the global maximum? So it starts from this point, and in which of these cases it will be able to reach the global maximum point. So in the first diagram, you can see that if it starts from here, it will go up to this point, and it will not be able to overcome this anymore. So this is a local maximum, and this is the global maximum. So it will get stuck in the local maximum point. In option B, it starts at this point. So it can go either towards right or towards left. If it goes towards right, then it can reach the global maximum point. If it goes left, it will get stuck to this local maximum point, and it will not be able to come out of it. So option B is also not right. In option C, it starts from this point, and there are no other local minima points in its path. So it will eventually go to this global maximum point. So option C is right. So question was that in which of these cases the EM algorithm will be able to achieve global maximum. So in option C, we can say that there are no other hurdles, so no other local maximum point, so it will reach global maximum. And in question in option D, so it starts at this point, it reaches this, and this is a local maximum point. So if this is local maximum, it will not be able to come out of this and reach this global maximum, so it will get stuck here in this local maximum, and so this is also not the right answer. So the only correct answer is question C. So this was the first question. So option C is the correct answer. Is it okay? So if there are any other questions or doubts, you can ask. What can we expect in the dynamic like what? So NPTEL final exams, we don't have any knowledge about that. We don't handle the exam papers or even anything related to the final exams. So it will be better if you ask in the discussion forum. So the regular TAs and the instructors should be able to answer your questions about the final exam. So you can ask your questions about this in the discussion forum. So the live session TAs don't have any knowledge about what kinds of questions would be asked or how many questions would be asked. So it's better to ask in the discussion forum. So thank you everyone. If there are no other questions or doubts, we can end this meeting here.